Chapter 21 is going to dive deeper into hypothesis tests, and it's very theoretical. It introduces a lot of different terminology. It tends to be a confusing chapter. One thing I found is that students understand it a lot more after we've done a few problems. So if you find that this chapter is particularly confusing, I would suggest coming back to this video notes after we've done a few days of problems in class to see if that helps clear everything up by watching it once you understand the terminology a little better. Let's say we're conducting an experiment to test the fairness of a coin and it results in a z-score of 0.62. What would we conclude? Since we're talking about a coin being fair, we would expect 50-50 results, and our null hypothesis would be p equals 1/2 or 50%. The alternative would be that this coin is producing results in some other proportion that's not 50%. So in our normal curve, if we put the proportions on the normal curve, 50% would be right in the middle. It's giving us the z-score of 0.62, and when we're talking about z-scores, 0 is always in the middle. So 0.62 is our z-score. Is that extreme enough for us to say this coin is not fair? We think that it's unfair and producing results at something other than 50%. Now, if the coin was actually fair, any results on this side, so let's say if we had gotten 55 out of 100 heads, it would be just as likely to get the same thing on the other side. So in other words, it'd be just as likely to get 45 out of 100 heads. So when we have two-tailed hypothesis tests when there's a not equal to sign here, we always double whatever probability we get from the first tail. So we would find our test statistic, find the probability of that, and then we're just going to do 2 times that probability to get our p-value. For every problem we've done so far, we've been using 5% as the threshold for a rare event where we reject the null hypothesis and decide that whatever we saw was unlikely to happen by chance alone. Sometimes we want to be a little more or less forgiving, and we can change the definition of this rare event by assigning it an alpha level or a significance level. And this is denoted by the Greek letter alpha. So for example, let's say we're doing a hypothesis test and we want to require a bit more proof to reject the null hypothesis. We might decide to assign an alpha level of 1% rather than 5%. So for this problem, for us to reject the null hypothesis, we would want to see our p-value drop below 1% instead of the traditional 5%. If that happens, we reject the null hypothesis. We say the results are statistically significant. If it doesn't happen, if we end up with a p-value of, say, 2%, when our alpha is 0.01, we would say, fail to reject the null hypothesis, there's insufficient evidence, etc., etc. We can also use confidence intervals to evaluate hypotheses, and we've done this before. We want to see if a number is within the interval or outside the interval. And confidence intervals go hand in hand with two-sided tests because confidence intervals are themselves two sides. Okay, they cut off the right tail and the left tail, and we're looking just at the middle. So a 95% confidence interval corresponds with a two-sided test at a 5% alpha. Okay, one-sided hypothesis tests, it gets a little harder to match up with a confidence interval. So for example, a 90% confidence interval corresponds with a 5% one-sided test. Reason being, if we look at this 5% hypothesis test here on the right, okay, we have 5% all on the right side. This would match up with a 90% confidence interval because there's 90% in the middle here. It stops right here, and this 5% on the left kind of just gets thrown away and ignored. We don't care about it. For example, a 90% confidence interval for the proportion of bullseyes shot by an archer is 29% to 45%. The archer previously averaged 30% bullseyes. Can we conclude that the archer is now shooting more than 30% bullseyes at an alpha of 0.05? So our hypotheses would be null hypothesis, the proportion is still 30% bullseyes. Alternative is that she's increased her proportion of bullseyes above 30%. Now, this is a right-tailed test because our alternative hypothesis says we want this to be greater than, to the right. Okay, so when it says up here that the alpha is 0.05, all 5% goes on the right side. So what that really means is we would find a test statistic when we do a hypothesis test, and we would get a z-score. Okay, and if the z-score ends up in that red shaded region, which is anything to the right of inverse normal 0.95, okay, which would be 1.645. So anything above that, we would reject the null hypothesis. Now, we're talking about a confidence interval. Okay, and for a confidence interval, these are all two sides. Okay, so we have the right side here, but we also have a left side that we don't really care about, and that's cutting off the same amount of area on the left. So in between these two is 90%. Okay, now we need to make sure that these confidence intervals and hypothesis tests match up with their alpha levels. Conveniently, we're given a 90% confidence interval. So when we look at these two things, we can compare them directly, and we can just look at this interval and say 30% is within this interval. Because of that reason, we can't reject the null hypothesis. It's possible that the archer is still shooting bullseyes 30% of the time. We would want to see 30% outside of that interval, like something like this at the bottom here, where it goes 31% to 45%. In that case, we would say 30% is unusual. She has increased her rate of bullseyes above that. Now, sometimes we do a hypothesis test and we do everything correctly, but we still make the wrong decision when it comes to rejecting or failing to reject the null hypothesis. And that's okay. We expect it to happen sometimes because natural sampling variation will sometimes fool us into making that wrong decision, such as rejecting a null hypothesis that's actually true. So there's two types of errors that we can make. The first one's called a type 1 error. This is the first type of error we can make. And the reason it's the quote unquote first type of error is that throughout the duration of a hypothesis test, we always believe that the null hypothesis is true. So in a type 1 error, the null hypothesis actually is true and we mistakenly reject it. The type 2 error is the reverse of that. The null hypothesis is false and we fail to reject it. Down here at the bottom, we see a little display. Some have our error type. So this we have a true null hypothesis, but it's rejected. Here we have a false null hypothesis. They use the wording retain, but we never want to use that. We would say fail to reject it. And then these other two situations are where we've made the right decision. False null hypothesis that's rejected. True null hypothesis that's failed to reject it. This situation right here is a particular situation, which leads us into the next slide. This is where the null hypothesis is false, and we have rejected it. The ability of a test to correctly reject a false null hypothesis is referred to as the power of the test. Now, there's probabilities that go with each of these error types and the power. Type 1, for example, is when we reject a true null hypothesis, and this is going to occur with the probability of whatever our alpha level is. So if we're working with an alpha level of 5%, we're going to make type 1 errors 5% of the time. Type 2 errors are a lot more difficult to assign a probability to, because really to do that, we need to know what's the actual value of the parameter. In most cases, we don't know that. So we use the variable beta to represent the probability of a type 2 error. Now let's backtrack a minute. The power of a test is the probability that we correctly reject a false null hypothesis. A type 2 error is when we fail to reject a false null hypothesis. These are complementary events. They add to 100%. Now I had mentioned that the probability of a type 2 error is assigned to this variable beta. And since it's complementary with power, the probability of power is 1 minus beta. The power of a test is also greater when the true population proportion lies far from the null hypothesis value. Let's say we're testing a die, okay, and we want to see, is this a fair die? Is it returning 1/6 sixes, let's say? Okay, if this die is really unfair and it's giving half of the results as sixes, that's going to be easier to spot than if it's just slightly biased. Maybe it's 1/5 instead of 1/6. So this is called the effect size. The larger the effect size, the larger it is from our null hypothesis value of p equals 1/6. The easier it is to spot, the higher the power is. So obviously we don't want to get these error types, but they will both happen at least part of the time. Another drawback is that we can decrease one of them, but that's automatically going to increase the other. For example, type 1 errors are going to occur at whatever our alpha level is. So if we have an alpha level at 5%, we're going to get type 1 errors 5% of the time. We can decide to change our alpha level to 1%. This vertical line will move over, and now we get less type 1 errors. But with that change, beta increases because that line is affecting both of these curves here. So the probability of type 2 errors increases when we change our alpha level. And with that, power is also going to get lower because that's also affected by that alpha level. Okay, so there's a trade-off with all these. One way that we can affect all of them at the same time, lower our error rates and increase the power, is by decreasing the variability in the samples. When you see this phrase, you need to be able to associate it with increasing the sample size. Decreasing variability makes the curves narrower. We do this by taking a larger sample, and when the curves get narrower, you can see that there's less area in those tails that represent the error rates, and there's more area in that part of the curve represented by power. All that being said, here's what one of these problems will look like. You and your friends apply for jobs at a local business. You're all rejected, and notice that the new hires are all the opposite gender. If you can prove gender discrimination, you plan to hire a lawyer and sue, so you take a random sample of 50 employees and record their gender. Hypotheses would be p equals 0.5. P is not equal to 0.5. This is representing the company hiring men and women equally, and the company not hiring equal genders. For these types of problems, I always find it helpful to write out verbal descriptions of my hypotheses. So part B is asking, what's a type 1 error? Type 1 error is the first type of error we can make. Now, for the entirety of a hypothesis test, we're assuming that the null hypothesis is true. So the first type of error that we can make is when we reject a true null hypothesis. Now, if we reject this, we would conclude that the company does not hire men and women equally, but that would be a mistake. So type 1 error would be concluding that the company is discriminating based on gender, when in actuality, they aren't. Right? We always want to write these in the context of the problem. Now, a type 2 error is the reverse of that one. It's when we have a null hypothesis that's actually false, but our p-value isn't small enough to actually reject it. And in this situation, we would continue to believe that the company hires men and women equally. So a type 2 error would be concluding that the company is not discriminating based on gender when they actually are. And they like to pair these error type questions with one of these two other types of questions. First, which of the two errors has more severe consequences? There's always consequences associated with both, but usually one is more severe. For example, it had mentioned in the text of the problem that you were contemplating hiring a lawyer if you were found they were discriminating. Now, that's a decision made in error. They're actually not discriminating. So you would go out, you would hire a lawyer, you would then lose the lawsuit and waste a bunch of money. Last part, name two ways we could increase the power of the test and explain the drawbacks of each. So first way we could increase the power is by increasing the alpha. So if we used a 10% alpha instead of a 5% alpha, we're going to reject more null hypotheses just in general. If we reject more null hypotheses, we're going to reject more false null hypotheses just by a matter of chance. Okay, now as we increase alpha, that's going to increase type 1 errors. That's the drawback. The other way we can increase the power is by increasing the sample size. Of course, this is going to be more expensive.